Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at some interesting functions of multiple random variables. I'm going to approach today's lecture as a collection of examples, but there's going to be some new material that we're going to cover, so please make sure you take good notes and pay close attention. All right. First thing. Very early on, I made a passing comment to you that the Gaussian random variable and the Rayleigh random variable are related to one another. I'm going to demonstrate that relationship today. So, first example, how the Gaussian and Rayleigh random variables are related. Do this as an example. So, let's look at random variable z, which is going to be the square root of random variable x squared plus random variable y squared. All right? And I'm going to assume that my joint random variable for x and y is a joint Gaussian, looks something like this. Looks something like that. And you'll notice that my PDF here is separable in x and y. Therefore, x and y are independent. More specifically, I could write my joint probability density function this way. Alright, this would be the marginal probability density function for x, and this would be the marginal probability density function for y. Alright, so when I have a function of two random variables that can be, or a probability density function for two random variables, which can be written as the product of marginal probability density functions, that means that those random variables are statistically independent. So that's the first thing, that how the Rayleigh and the Gaussian random variables are going to be related. We're going to be looking at Gaussian. You'll notice for both x and y have zero mean. All right, there's zero mean random variables, and they have the same standard deviation. So what I mean by this is that the mean for x equals the mean for y equals 0. The standard deviation for x equals the standard deviation for y, and they both equal sigma. All right, so if you were looking down at this joint probability density function, and I really can't draw in 3 dimensions here, but if that was the x direction and that was the y direction, what you would find is a circularly symmetric function centered at the origin. All right, this function here is circularly symmetric. Centered at the origin. All right, so first thing in looking at how the Gaussian and Rayleigh random variables are related, we've got two statistically independent random variables, x and y, two statistically independent random variables, x and y. They both have zero mean, and they have common standard deviation. First thing. All right? All right. Let's find the cumulative distribution function for z. The cumulative distribution function for z is the probability that z, which equals the square root of x squared plus y squared, is less than or equal to some little value z. And this is equal to, let me write this down, r sub z here, my limits of integration, this is sort of a shorthand. I'm going to simplify this for you in just a second. This is a circular area bounded by the circle z equals x squared plus y squared. And of course z is a variable, so as z increases, the circular area over which I'm going to integrate my joint probability density function increases. All right, that's kind of hard to do in rectangular coordinates. Let's put it in polar coordinates. Let me start over here on the right hand side. This can be written in polar coordinates as integral from 0 to 2 pi, integral from 0 to z. And by the way, you'll notice here that z, in this case, z is always positive. All right? That's why I'm going to integrate z from 0, I'm going to integrate radially from 0 up to z. Continuing with my integral, my integrand is 2 pi sigma squared e to minus r squared over 2 sigma squared r d r d, not sigma, d theta. All right, we're talking polar coordinates here, so r equals x squared plus y squared in polar coordinates. That's my distance r, and that angle is theta. Okay? All right, next thing I'm going to do is I'm going to make a change of variables. I'm going to let u equal r squared over 2 sigma squared, du equals r dr over sigma squared. And I'm going to first integrate against theta. You'll notice that my integrand here is not a function of theta, so when I integrate against theta, I just multiply everything by 2 pi. That makes my 2 pi go away in the denominator. So I get integral from 0 to z. I'll do my change of variables in just a second. 1 over sigma squared e to minus r squared over 2 sigma squared. Let's make that an r dr. Now we'll do my change of variables. And this becomes integral from 0 to z squared over 2 sigma squared e to minus u du. Integrating this, I get minus e to the minus u, evaluated from 0 to z squared over 2 sigma squared. And this becomes 1 minus e to the minus z squared over 2 sigma squared. And then at the last step I have to throw in a step function because z is always greater than 0. Z is greater than or equal to 0 in cases. Alright? Well, hopefully you will recognize this as the Rayleigh cumulative distribution function. This is the Rayleigh CDF. All right? The cumulative distribution function for z, which equals sum of x squared plus y squared, where x squared and y squared are independent, zero mean, Gaussian random variables, I get a Rayleigh. What about the probability density function? Let's remind ourselves what the cumulative distribution function is. The CDF was this, 1 minus e to the minus z squared over 2 sigma squared u of z. Take the first derivative of that to get the PDF. And I get z over sigma squared e to the minus c squared over 2 sigma squared. Once again, the step functions don't come out of either the integration or derivative process. I just have to be clever and notice that z is always positive and throw that back in. Well, once again, this is the Rayleigh PDF. And this is the Rayleigh CDF. And just to remind you what the Rayleigh probability density function looks like. That's that. My step function means that it has no value less than 0. It's going to look something like that with a long declining tail. The peak is at sigma. The maximum value right there is 1 over sigma times the square root of e. From our previous work, the mean value is sigma times the square root of pi over 2, and that's about 1 1/4 sigma. So the mean is maybe about right there. All right, it's 50% likely to be above the mean, 50% likely to be below the mean. And the reason that the mean is a little bit to the right of the peak value is because this long upper tail extends to infinity. So there's a lot of area up there. For the Gaussian, we also saw this. The mean squared value is 2 sigma squared, and the variance is, this is from a long time ago, this is the mean squared value minus the square of the mean, and that is 2 minus pi over 2 sigma squared. That's just sort of as a reminder. Okay? So that's how the Gaussian and the Rayleigh random variables are related to one another. All right. First example done. Now let's look at what happens when we add. Approach this again as another example. What happens when we add statistically independent random variables? Z is the sum of x and y, and x and y are statistically independent. What I want to know is, what is the probability density function for z in terms of the probability density functions for x and y? All right. I'm going to start by finding the cumulative distribution function, then I'll later take the derivative. Cumulative distribution function for z equals the probability that z, which equals x plus y, is less than some specified value little z. All right. Let me write down the next step, and then I'm going to draw a figure to make sense of what I'm trying to do here. This can be written as, again, hang on just a second, y equals minus infinity to plus infinity. This is the complicated one. X equals minus infinity up to z minus y. Of my joint probability density function. All right. So what am I doing here? It's the limit on x that's really the somewhat confusing point. So let's look at x and y. That's supposed to be a straight line with a slope of 1. This line is where x plus y equals z. So if x equals 0, y equals z. If y equals 0, x equals z. So that boundary there is x plus y equal to z. That means that this region down here is the region for which x plus y is less than or equal to z. All right? That's the region over which we want to integrate the joint cumulative or joint probability density function. All right? Now what I'm going to allow is I'm going to allow y to go from minus infinity all the way to plus infinity. But when I do that, x is limited. For any value of y, for example, right there, my maximum value for x is right there. All right? So for a given value of y, the max value maximum value of x is y minus z, or z minus y rather. All right? That's why in my integral over here I'm going to allow y to go from minus infinity to plus infinity, but x is going to go from minus infinity up to z minus y. That's what that's all about. Okay? All right. Moving right along. Let's continue with my integral here a little bit. I'm going to use now that my joint probability density function is separable, because I'm talking about statistically independent random variables. This is going to be integral from minus infinity to plus infinity. Integral minus infinity to z minus y. fx, y dy. All right. Let me jump to the next page, and what I'm going to do next, I'm going to jump right to the probability density function being the first derivative of my cumulative distribution function. All right, let me just jump to the next page to do that. My probability density function for z, remember z is the sum of statistically independent random variables. This is oops. All right, so what I'm going to do is I'm going to integrate first against x. When I integrate against a variable, I lose that variable in the result. So when I integrate, when I perform that integration right there, the result is not going to be a function of x, it's going to be a function of z minus y. That means that that portion of this composite integral here is going to be what's a function of z. It's this integral result right here that's going to be a function of z, and that's what I'm going to take the derivative of. And then I'm going to integrate against y. All right. This then becomes, where am I? Negative infinity to plus infinity. Derivative with respect to z of all right. So when I integrate a probability density function, I get a cumulative distribution function. All right. So this becomes and you'll recall that the cumulative distribution function evaluated at minus for any random variable equals 0. All right. So now here I have a function of z. Take that derivative, and I get integral from minus infinity to infinity. And that is my result. All right. I hope that all of you viewing this video will recognize that result as a convolution integral. That is a convolution integral. All right. Shorthand notation is commonly this. That little asterisk means perform the convolution integral. All right? Don't worry. Don't freak out. I'm not going to make you do any convolutions by hand. MATLAB is very happy to do convolutions for you, and I'll allude to this a little bit more in just a few minutes. But MATLAB has a really nice function, conv.m, convolution. So if you give MATLAB a vector in x and a vector in y and plug it into the conv function, it's very happily does convolutions for you. All right, so what we find, let's go to the next page. All right, z equals x plus y, x and y independent. What I find is that if random variable z is the sum of two statistically independent random variables, what I find is that the probability density function for z is the convolution of the PDFs for x and y. And you'll notice that I've solved this in a very general fashion. I haven't said what probability density function for x or y are. It doesn't really matter. It's always just a convolution as long as z is the sum of statistically independent random variables. By extension, if z equals x1 plus x2 plus x3 plus xn, and all random variables x sub I are statistically independent, then the probability density function for z is always just the composite convolution. If a random variable is the summation of any number of statistically independent random variables, then the probability density function for z is the composite convolution of all of the statistically independent probability density functions. All right? There's something remarkable happens. Turns out, and this is unexpected and very important, this becomes approximately Gaussian. And I'm going to demonstrate this by example in just a minute. All right, the remarkable thing, and I'm stating this without proof, I'm going to demonstrate it by example in just a minute. The remarkable thing is that if I add up a bunch of statistically independent random variables, meaning that the probability density function for z is the composite convolution of the PDFs for those independent random variables, it turns out that the probability density function for z approximates a Gaussian very, very, very closely. And you'll notice that I haven't said anything about the nature of the probability density function for x1 or x2 or x3. One of them could be a Gaussian, one of them could be a Rayleigh, one could be a Cauchy, one could be exponential, maybe perhaps even one might be a discrete probability density function. It doesn't matter. The only thing that matters is that they are statistically independent and I add them together. the composite probability density function for Z approximates a Gaussian. All right, it's really quite extraordinary, and it's not something that is obvious. So let's do this by example. Let's demonstrate this by example. So I'm going to assume that I add together 4 statistically independent uniform random variables. Add together 4 statistically independent uniform random variables. We'll add together 4 statistically independent uniform random variables, and we'll assume that they all have the same PDF. We'll assume that they all have the same PDF. It's not required. To get an approximate Gaussian, I only have to add together a number of statistically independent random variables. I'm assuming, just for simplicity's sake right now, that I've got 4 that are uniform and have identical probability density functions. All right. We're going to assume that the PDF for each of them looks something like this. Here I equals 1, 2, 3, 4. All right. Mathematically, oops. That's that. All right. All right. Now, if we consider 2 of them together, what I'm going to first do is I'm going to convolve 2 of them. I'm going to let Z1 equal x1 plus x2, Z2 equal x3 plus x4, and then later on the composite random variable Z will be Z1 plus Z2. All right. So hopefully you have seen some simple convolutions earlier on. When I convolve a rectangle function, I get a triangle function that's twice as wide. All right? Let me just draw this out for you. All right. Mathematically, my probability density function for Z1 and Z2 looks something like this. 1 minus absolute value of Z sub I and 0. And this is true for I equals 1 and 2, where at this point I'm talking about Z1 and Z2 here. All right. So remember how you do convolution. When you convolve 2 functions, you take one function and you flip it backwards. You reverse it. Well, a symmetric rectangle function about the origin, like we have here. When I flip that, mirror image, it looks exactly the same. And then what I do is I slide one function past the other and I integrate the overlapping areas. So when I take a rectangle function and I convolve it with another identical rectangle function, my overlapping area increases up until they overlap fully. All right, and then it trails back off. As I slide one function past another, the overlapping area increases until they are overlapped fully, and the overlapping area is 1. And then as they continue to slide past one another, the overlapping area decreases until they pass one another. The overall width of the convolution is twice as wide as the rectangle function. Okay? So that's that. Now, I still got to get to there. All right. Without proof. When I take Z1 equals, Z, let's try again. When I take Z equals Z1 plus Z2, F Z equals F Z1 convolved with F Z2. All right. What I'm doing here is I'm convolving two triangle functions. All right. To get to the composite probability density function for Z, to get to the composite probability density function for Z here, since I'm adding Z1 and Z2, what I'm going to have is the convolution of two of these triangle functions. You can find this in textbooks. I'm just going to write the result down, and then I'm going to discuss the results and tell you how you might do it a little bit simpler. So it turns out, without proof, my composite probability density function is this. It's a mess, but let me write it down, and then we'll talk about how to do it simpler using MATLAB. Oops, that's supposed to be a 2. Right, so the third power. And this is for 1 less than or equal to Z less than or equal to 2. All right, and you'll notice that over here I've written the limits for positive Z from 0 to 2, and this is actually symmetric about Z equals 0. Okay? All right? All right. So, I started off with 4 statistically independent uniform random variables that extend from -0.5 to +0.5. I convolve 2 of those together and I get a triangle function that extends from -1 to 1. I convolve the 2 triangle functions and I get a result that extends from -2 to +2. All right. Here's the result. All right. Let me piece this together for you. First of all, I have made available to you a MATLAB M file that I wrote to calculate all this. It's called Sum of Independent Random Variables. It does this example of adding together 4 statistically independent uniform random variables. On the left-hand side, over here, I'm plotting FZ1 and FZ2. This is the result of convolving 2 two rectangle functions, and I get out my triangle function. Over on the right-hand side, I have the result of convolving all four of my probability density functions together. You'll notice that the blue curve is f sub z of z, and my red curve is an ideal Gaussian Okay, so how did I do that? All these calculations were done in the MATLAB program, sum of independent random variables.m. All right, first of all, I did not, in my MATLAB program, I didn't use this result. I used the conv, C-O-N-V function. In my MATLAB program, I used Okay, that's the first thing I did. I used the CONV function to get my composite probability density function. I created a vector of values and created in MATLAB the triangle functions, and then I used the CONV function to convolve the triangle functions. Unless you download and take a look at the lines of code in this sum of independent random variables M file, a lot of what I'm saying is going to be a bit confusing. Please do download it. I created a vector of values for my triangle functions, and then I used the CONV function to get the composite probability density function. I also, in MATLAB, I found that the standard deviation for the composite probability density function was a third. All right, I did that in MATLAB. And those steps are in there. I showed you how to calculate. A few lectures back, I showed you how to write some MATLAB code to find the standard deviation for probability density functions that you were modeling numerically. So I found in MATLAB that the standard deviation for this guy is a third. And then what I did, and you'll notice over here that it's always zero mean. So what I did then was I plotted an ideal zero mean Gaussian with sigma of 1/3. That's where I got my ideal Gaussian over here. My ideal Gaussian here is just this. That's just that. That's a zero mean probability. That's a zero mean Gaussian probability density function, and I let sigma be 1/3. All right. I calculated that all numerically in the MATLAB program that I've given you. Okay. And what we see is I started off with 4 statistically independent uniform random variables. A uniform random variable doesn't look much at all like a Gaussian random variable, but when I convolve only 4 of them together, I get a composite probability density function that is extraordinarily close to an ideal Gaussian. It's not quite perfect, but it's extraordinarily close. If I convolved many more statistically independent random variables, the blue curve and the red curve on the right-hand side of this page would be virtually indistinguishable from one another. Okay, so I haven't proven to you this statement at the bottom of the page. I haven't proven that to you, but I think I've demonstrated it pretty well by example. All right. Again, for you to really understand what I'm doing here, I need you to download and study the steps in that sum of independent random variables M file. let's extend this concept and formalize it a bit. There's a thing called the central limit theorem. Central limit theorem. It's a very important concept, and it's pretty slick. So we're going to let x1, x2, x3, all the way up to x sub n be a collection of statistically independent random variables statistically independent random variables with means mu, let's just use little m for now, make my life easier. Means m1, m2, all the way up to m sub n, and standard deviations sigma 1, sigma 2, sigma n. All right, respectively. All right. Then, if I add them together in a normalized fashion, this way in particular, z equals 1 over square root of n, summation I equals 1 to n, x sub I minus m sub I over sigma sub I. This is a new random variable. This thing, when I add together my statistically independent random variables in this normalized fashion, what I'm first going to do is I'm going to make them all zero mean by subtracting the mean value. And then I'm going to divide by the standard deviation, add them all together, divide by the square root of n. Turns out that this new composite random variable z approaches a zero mean unit variance Gaussian random variable. All right? And this is true at least as n approaches infinity. All right? So what the central limit theorem says is if I have a bunch of statistically independent random variables and I add them together in this normalized fashion, as I'm shown here, subtract off the means, divide by the standard deviations, add them all up, divide by the square root of n, turns out that that new random variable z, this one, approaches a zero mean unit variance Gaussian random variable as n approaches infinity. It means that the PDF for z is a zero mean unit variance Gaussian. All right? The approximation generally is best if n is greater than or equal to, say, 30. Once you get above 30 independent random variables, then the zero mean unit variance Gaussian approximation gets really, really, really good. Let me write some stuff down here in the corner. The PDFs for each x sub I can be anything. The PDFs for each x sub I can be anything. One could be Gaussian, one could be Rayleigh, one could be uniform, one could be delta, discrete. It could be anything. They just have to be statistically independent. And another thing, for this to converge more rapidly to a zero mean unit variance Gaussian, we generally like to see that all of the standard deviations for the various random variables are roughly on the same order. We don't want one random variable to dominate too much over the others. We don't want one to be a width of 100, a standard deviation of 100, while the rest of them are on the order of a standard deviation of 1 or 2. If that was the case, then we would have to add together a lot of random variables in order to approach this zero mean unit variance limit. But generally speaking, if we've got about 30 or more independent random variables, and the standard deviations are roughly on the same order, regardless of what the probability density functions for each x sub I random variable are, we get something that's very closely zero mean unit variance. All right, let's do an example. Got a company that makes gear pins. Got a company that makes gear pins. All right. L sub I is a random variable describing the length of individual gear pins. All right. This is a special case. We're going to assume that the PDFs are unknown. We're going to assume that the PDFs for the length, the PDFs describing the length of individual gear pins is unknown. We don't have any idea, and we really don't care for this particular example. We are going to assume that whatever they happen to be, we're going to assume that the probability density functions describing the length of each individual gear pin are identical. By that I mean shape the same, whatever it may be. Means and standard deviations same. Okay? I don't know what the shape of the individual gear pin probability density functions are. I'm just going to assume that they're identical, meaning they have the same shape, the same means, and same standard deviations. All right? After extensive testing, Alright, so there's some poor soul who stands at the end of the assembly line, and he or she has a set of calipers, and they have measured the length of gear pins coming off that line for the decades. And we know that the mean length is 10 millimeters, and we know that the standard deviation is 0.1 millimeters. Pretty tight tolerances. All right. So after lots of testing, we've discovered that the mean length of my gear pins is 10 millimeters, and I have a standard deviation of 0.1 millimeters. And oh, by the way, I need to say this, that we're going to assume for this example that all of my gear pins are manufactured independently. All right. We're going to assume that all of my gear pins are, the length of one gear pin coming off the line is, we're going to assume that it's independent of the rest. And here's the question we're going to answer. What is the probability What's the probability that the mean sample length L bar of n randomly chosen pins differs, it's an important word, differs, could be too long or too short, differs by more than 0.1 standard deviations from the true mean length, true of 10 millimeters. Okay? All right. So that's a question. And the way this is written, we use the word differs. So the question is, what is the probability that a collection of n randomly chosen gear pins, I measure their length and come up with a sample mean L bar. What's the probability that the sample length L bar of n randomly chosen gear pins is either greater than the mean length by at least 0.1 standard deviations or shorter than the mean length by at least 0.1 standard deviations? That's a question we're trying to answer. All right. Let's write down my random variable from the central limit theorem. All right. Now what I'm going to do is I'm going to pull out my standard deviation, and I can do this only because I'm assuming that the probability density functions for each, for the probability density functions governing the length of each individual gear pin are identical, meaning shape, mean, and standard deviation. I get this, I get 1 over sigma L square root of n Okay. You'll notice a couple things here. First thing I did was I pulled out sigma sub L because that's identical for all of the gear pins. That's not a function of little I, so I just pulled that out. I also, my true mean length is constant for all those gear pins, so I just added it up n times. That's how I got that far. All right. So only L sub I remains inside of the summation at this point. All right. Now what I'm going to do is I'm going to multiply and divide by the square root of n, and I get square root of n over sigma L times 1 over n summation I equals 1 to n L sub I minus mu sub L. Now you'll notice this, I just add up the gear pin lengths and divide by the number of samples. That right there is L bar. That's my mean sample length. just dropped my pen. Sorry about that, folks. So I get this as my next step. All right. All right. That is my random variable z, my normalized random variable z. This is a special case. It assumes all individual PDFs are identical. Okay? That's what that's assuming. All right. Well, what was the question that was asked for us? The question was this. That was the question that was asked of us. We want to find the probability that the mean sample length differs from the true mean length by greater than 0.1 standard deviations. Remember that differs by means that my mean sample length can either be too long or too short. Thus, my absolute value symbols here. All right. So let's take this the next step. I'm going to multiply times square root of n over sigma. Need my absolute value sign. All right. Oops, I'm sorry. That is a sigma sub L, and I need over here a square root of n. There we go. I'm multiplied by square root of n and divided by sigma sub L. All right, let's go to the next page and finish this up. Let's remind ourselves where we are. P naught equals the probability that square root of n over sigma L bar minus mu L is greater than or equal to 0.1 square root of n. Now I'm going to get rid of those absolute value signs. And I can do it this way. This is the probability that z equals square root of n over sigma L bar minus mu L is greater than or equal to 0.1 square root of n plus probability that z equals square root of n over sigma, oops, I forgot my sub L's here. That's that. Okay. You'll notice that up here, I was not indicating that the stuff that I just underlined in red was equal to z because z does not have absolute values in it. The next step, I got rid of my absolute values so I could equate square root of n over sigma sub L times L bar minus mu sub L. I can equate that equal to z, and we'll remember that z is a zero mean unit variance Gaussian random variable. In particular, PDF looks something like that. The standard deviation for Z is 1. All right. So you'll remember that this first probability right there is the integral over the upper tail. All right. So what we've got here is 0.1 square root of n. What I'm asking myself is integration of that upper tail. And integration of the upper tail for a zero mean unit variance Gaussian is simply the Q function. That's what that is. And by symmetry, the second piece, let's make this part blue, the second piece of my probability is the integral of the lower tail it's the area less than negative 0.1 times the square root of n, and by symmetry the area of that blue hatched area is also Q of 0.1 square root of n. Okay? Z is a zero mean unit variance Gaussian. When I integrate the upper tail or the lower tail of a zero mean unit variance Gaussian, I just get a Q function. So for that reason, that's my result for this particular problem. Okay? You'll notice that my answer is not a function of it's not a function of the true mean length, not a function of sigma sum L. It's not a function of the mean or standard deviation for the probability density functions governing the length of each individual gear pin. It's not a function of anything. It's only a function of the number of samples I examine. It's only a function of the number of gear pins that I select off the assembly line and examine. All right. Well, so let's calculate some results. I used, you can either use Q tables, like in the back of your book, or the Q.M file, MATLAB file I sent you earlier in the semester. But for this particular problem, remember, P0 equals 2 times the Q function of 0.1 square root of n. What I found was if n equals 10, P0 was about 75.2%. What that means is if I just look at 10 gear pins coming off the line, about 75% of the time the sample length, the mean sample length L bar is going to be greater than or less than the true mean of 10 millimeters by about 0.1 standard deviations. If I let n equal 300, I got P naught of about 8.4%. I was curious how many pins I would have to examine to get exactly 10%, and I fiddled and fiddled and fiddled with it. Very scientific process. I came up with 271. Gave me a 10% chance of my sample length being too long or too short by 0.1 standard deviations. If I let n equal 1,000, I got P naught was about 0.2%. And of course, if you plug in infinity, I get P naught is exactly 0. All right? So if I pull 271 pins off of my assembly line, randomly selected, and measure the length of each one, find the average of the sample, 90% of the time, the mean sample length is going to be less than 0.1 standard deviations away from the true mean of 10 millimeters. All right? And as you might expect, the more samples I collect, the closer the sample mean is to the true mean. All right? Well, that's all I have for today, folks. As usual, if you have any questions, please contact me at your earliest convenience, and I will do my very best to answer all your questions as fully as possible. Have a nice day. Bye-bye.